Let's look at a problem involving an N-type silicon bar. We are told the bar has a length of 0.1 centimeters and a cross-sectional area of 100 square micrometers. In this material, the concentration of majority carriers, which are electrons, is 5 times 10 to the power of 20 per cubic meter. We are also given the electron mobility represented by the Greek letter mu, which is 0.13 meters squared per volt-second. Finally, we know the charge of a single electron is 1.6 times 10 to the power of negative 19 coulombs. Our goal is to calculate the total electrical resistance of this specific silicon bar. Before we solve, let's understand what these terms mean. An N-type semiconductor is simply silicon that has been doped to have extra electrons. The carrier concentration, or N, tells us how many free electrons are available to move. The mobility, or mu, describes how quickly and easily an electron can move through the silicon when an electric field is applied. Think of it like how easily a car moves through traffic. To find the resistance, we first need to figure out how well the material conducts electricity, which is called conductivity, and then determine its resistivity, which is the opposite of how well it conducts. Step 1 is to calculate the conductivity denoted by the Greek symbol sigma. Conductivity tells us how much current the material can carry. For an N-type material, we find this by multiplying 3 things together: the number of electrons, the charge of one electron, and the electron mobility. By multiplying 5 times 10 to the power of 20 by the electron charge and by the mobility of 0.13, we get a conductivity of 10.4 Siemens per meter. This value represents the material's inherent ability to allow flow. The higher this number, the easier it is for electricity to pass through. Step 2 is finding the resistivity denoted by the Greek symbol ρ. Resistivity is simply the mathematical inverse of conductivity. While conductivity measures how easy it is for current to flow, resistivity measures how much the material resists that flow. To find it, we divide 1 by our previous answer of 10.4. This gives us approximately 0.0962 ohmmeters. This is a characteristic of the material itself, regardless of its shape. Once we have this resistivity value, we can finally factor in the physical dimensions of our specific bar, its length and its thickness, to find the actual resistance. In the final step, we calculate the total resistance, R. Resistance depends on the material's resistivity multiplied by its length and divided by its cross-sectional area. We must be careful to use standard meters for all units. We convert the length to 10 to the power of negative 3 meters and the area to 100 times 10 to the power of negative 12 square meters. After plugging these into our formula, we get 0.962 million ohms. This is approximately 10 to the power of 6 ohms. Therefore, the correct answer is option A. This bar provides a high level of resistance due to its very small cross-sectional area.